Now let us come to the GATE 2020 chemistry question number 45. Here in this question they have given 8 structures, and all these 8 structures contain various types of C double bond O, and the question is, by after investigating these 8 structures, we have to answer the total number of compounds showing C double bond O stretching frequency less than 1700 centimeter inverse in their IR spectra. Now, in order to answer this, first we have to know what are the C double bond O which shows the stretching frequency below 1700 centimeter inverse. Now, I would like to highlight the 3 cases where usually C double bond O stretching frequency will appear at below 1700 centimeter inverse. Number 1 is if the carbonyl is a conjugated carbonyl. Number 2 is if it is amide. And number 3 is if it undergoes the strong hydrogen bonding. These 3 factors we have to take into consideration, and we have to apply all these 3 into the given 8 structures in order to understand which structures will show below 1700 centimeter inverse C double bond O stretching frequency. Now let us try to cancel few structures out of 8. Now I would like to cancel 5 structures out of 8. Now let us see based on how we are cancelling. The first one is the cyclopentanone, because we know that C double bond O of cyclopentanone gives peak at 1750 centimeter inverse, because it depends on the size of the ring. If size of the ring increases, then nu bar C double bond O decreases. Now the next one is the conjugated ester. That conjugated ester usually appears at 720 centimeter inverse. It cannot give the peak at below 1700, which is the question asked. The next one is the acid chloride. That is usually acid chloride appears at 1780 to 1800 centimeter inverse. As because this C double bond O is in conjugation with phenyl, so it is expected that it will be less, but at any cost it will not come below 1700. Now the fourth one I would like to cancel is one ester, because it appears at 1740 to 1750 centimeter inverse. And so after cancelling these 5 structures, there are 2 esters are there, so total 5 are cancelled. So the leftover 3 structures will give the peak at below 1700, it is expected. Now let us see who are they. Number 1 is the conjugated ketone. The conjugation is with the benzene ring, so this can appear at below 1700. Next one is the conjugated ester, but it is not a simple conjugated ester. That ester C double bond O also participates in the intramolecular hydrogen bonding, because that compound has OH group ortho with respect to C double bond O, and the name of that compound is the methyl salicylate. So this is the second compound, and the third compound is also a conjugated ketone. So therefore these 3 structures out of the 8 structures will give the C double bond O stretching frequency at below 1700 centimeter inverse. Now let us discuss the question number 51 of GATE 2020 chemistry. The numerical is like this: assuming no interaction between vibrational and rotational energy levels in HF, the frequency in centimeter inverse of R branch line originating from J is equal to 4 in its IR spectrum is. Additional information given to solve this problem is rotational constant, or B for HF, is equal to 19.35 centimeter inverse, and nu bar naught is equal to 4138.52 centimeter inverse. Now, in order to calculate this problem, we need to understand that what do we mean by the R branch line. Now, when IR light interacts with molecules, then we know that vibrational excitation happens from the ground state to the various excited states. Now, pure vibrational excitation is not possible. Any vibrational excitation is accompanied by rotational excitation also. So, if we consider the vibrational excitation from the ground state having vibrational quantum number V is equal to 0 to the first excited state having vibrational quantum number V is equal to 1, then there will be some excitation related to the change in the rotational quantum number, and that is the basis of getting three different types of branch lines. One is called as the P branch, another is called as the Q branch, and the R branch is also there. Now, what is the criteria to get P branch lines, Q branch lines and the R branch lines? In our problem, it was asked to calculate the R branch line. So, let us begin with the R branch line. Now, if the delta J is equal to plus 1, delta J means difference in the rotational quantum number from ground state to the excited state. If it is plus 1, then that will give rise to the R branch. Means for V is equal to 0 to 1 transition, if the change in the rotational quantum number is 0 to 1, other is 1 to 2, other is 2 to 3 or 3 to 4 or 4 to 5, etc., means delta J is equal to plus 1, that will give rise to the R branch. Similarly, if there is no change in the rotational quantum number of the ground state to the excited state, means for V is equal to 0 to 1 transition, if the vibrational excitation happens with the no change in the rotational quantum number, means 0 to 0 transition, 1 to 1 transition, 2 to 2 transition, 3 to 3 transition, 4 to 4 transition, that is the origin of the Q branches. Similarly, like this vibrational excitation, if it is accompanied by rotational quantum number change, delta J is equal to minus 1, means 1 to 0 transition, 2 to 1 transition, 3 to 2 transition, 4 to 3 transition, etc. That is the origin of the P branch. Now for R branch, the frequency expression nu is equal to nu bar naught plus 2b j double prime plus 1, where nu is the frequency of the R branch line, nu bar naught is the only vibrational excitation frequency without any change in the rotational excitation, b is the rotational constant, j double prime is the rotational quantum number of the ground state. Now, a nu bar naught and the b, these values are given in the problem. Here nu bar naught is equal to 4138.52 centimeter inverse plus 2 into rotational constant 19.35 into j double prime means 4 plus 1. So, if we do the simplification of this, it is coming that 4332.0 centimeter inverse. So, therefore, the answer is 4332.0 centimeter inverse. Now, in the year of 2019, no question came on IR, so we are moving to the 2018 GATE question paper, question number 55. The strongest band observed in IR of the final product of the following reaction appears approximately at dash into 100 centimeter inverse. If we investigate that reaction is actually a 3,3 sigma tropic shift, a cope reaction. Here the non-conjugated diene under thermal condition will undergo 3,3 sigma tropic shift and we will get one dienol. And this dienol undergo the tautomerization and finally we will get the stable diketone. Now, if we record the IR spectrum of the final product which has the identical two ketones, so therefore it is expected that it will be having the peak at 1715 centimeter inverse approximately due to the isolated C double bond O, because there is no other factor like ring size or hydrogen bonding or conjugation, like that important factors are not there. So it is expected that approximately it will show the IR peak, obviously a strong peak at 1715 centimeter inverse. Now if we look at the question given, they are asking some value which can be multiplied by 100 centimeter inverse. Means that 1715 centimeter inverse we have to express in the form of the some value multiplied by 100 centimeter inverse. So if we do the necessary exchanges, then it comes at that value will be 1715 centimeter inverse will be 17.15 into 100 centimeter inverse. So the fill in the blanks given answer will be 17.15 centimeter inverse. In GATE 2017, no question was asked based on only IR. So let us move to the GATE 2016 chemistry question paper, question number 47. Now in this question they have given the three stretching or bending related to the carbon dioxide and labeled as structure 1, 2 and 3, and based on after investigating these three we have to comment on the IR active mode out of these three. Now there are options given A, B, C, D. Out of them we have to pick up the correct option. So structure 1 is related to the symmetrical stretching of carbon dioxide which is not associated with the any change in the dipole moment. So the one is IR inactive. Coming to the structure 2, there it is given the antisymmetric stretching of carbon dioxide which is IR active because there is a change in the dipole moment during this antisymmetric stretching of carbon dioxide. And the third one is the in-plane bending of carbon dioxide, and there also some change in the dipole moment happens. So therefore this in-plane bending of carbon dioxide is also IR active. So this is the structure 2 which is antisymmetric stretching, and the structure 3 which is in-plane bending of carbon dioxide. These two are IR active and this option is given in the option number D. So therefore the final answer is D. There was no question asked in the year of 2015 in GATE exam chemistry. Now we are switching over to the GATE 2014. Question number 3. The number of IR active vibrational normal modes of carbon dioxide is dash. Now in order to answer this question we have to know that number of normal modes of vibration of the linear molecule is equal to 3n minus 5, and the number of normal modes of vibration for non-linear molecule is equal to 3n minus 6. Carbon dioxide is a linear molecule, so therefore we have to use the 3n minus 5 formula, not 3n minus 6, where n is equal to number of atoms in one molecule, means in carbon dioxide n value is equal to 3. Now if we put it into this value 3n minus 5, then 3 into 3 minus 5 is equal to 4. Now these 4 normal modes of vibrations can be divided into two categories, put together stretching plus bending. Now we know stretchings are of two types, symmetric stretching and antisymmetric stretching. Now when the stretchings are 2, so therefore bending definitely will be 2 because 4 minus 2 is equal to 2. So these bendings will be equally divided, one in-plane bending and one out of the plane bending. Now in all these normal vibrational modes, of vibrations are IR active except that symmetrical stretching of carbon dioxide, because the symmetrical stretching of carbon dioxide is not associated with the change in the dipole moment. So therefore it is IR inactive, and the remaining three, there will be change in the dipole moment during all these vibrational excitations. So therefore these three are IR active, means the antisymmetric stretching of carbon dioxide, in-plane and out-of-plane bending vibration of carbon dioxide. So the final answer is 3. Now coming to GATE 2014 ke another question, that is question number 19. The correct order of IR stretching frequency of C double bond C in the following olefins. Now there are three structures given, and all are the cyclic compounds with exocyclic double bonds. Structure 1 has the 6-membered ring, structure 2 has the 4-membered ring, and structure 3 has the 3-membered ring. Along with this, there are 4 options A, B, C, D are available. We have to answer. Now in order to answer this question, what concept is required is the stretching vibration in IR is directly proportional to the strain of the ring. Means if strain of the ring is more, then the stretching vibrational frequency also will be more. And another important thing is the strain is inversely proportional to the size of the ring. Means lower the size of the ring, higher will be the strain, higher will be the stretching frequency. So by considering this concept, we will be able to understand that the structure 3 where the 3-membered ring is present, structure 2 where 4-membered ring is present, whereas in case of the structure 1 the 6-membered ring is present, the smallest ring is present in the structure 3. So therefore the strain is maximum, and that 3 will be having the maximum C double bond C stretching frequency, followed by 2, followed by 1. Now that option is available in the C's, so therefore C is the answer. Now let us move to the GATE 2013 chemistry question paper, question number 25. Among the compounds given in the option A to D, the one that exhibits a sharp band at around 3300 centimeter inverse in IR spectrum is A12-butadiene, B13-butadiene, C1-butene and D2-butene. Now in order to answer this question, first what we have to know is at 3300 centimeter inverse in IR which peak can appear. Now there are three options are there at 3300 centimeter inverse. OH stretching, NH stretching and the triply bonded CH stretching can appear. Now in the given options A to D, only one we have to pick up and none of them have OH and the NH. So we have to find out in given 4 molecules where we have the triply bonded CH, or in other words which of these A to D molecules represent terminal alkyne. Now if we see the structure A, B, C, D, then it is the structure C which is actually 1-butene and it is one terminal alkyne. Another alkyne is also there in option D, but it does not have the triply bonded CH, so our final answer is C. Let us go to discuss that another problem, question number 34 of GATE 2013. In this problem, it was asked actually the IR spectrum of HCl shows an absorption band centered at 2885 centimeter inverse. The 0-point energy of HCl molecule under harmonic oscillator approximation is. There are 4 options are there. Now in order to solve this numerical, we need to know what is the expression for the 0-point energy, means the energy of the lowest level if we consider the harmonic oscillator, means the vibrational excitation will obey the simple harmonic motion and there is no anharmonicity. Based on that, the harmonic oscillator will be having the energy expression EV is equal to V plus half into H nu, means where V stands for the vibrational quantum number of each and every vibrational level. If we put all these values of the vibrational quantum level, we will be getting the energy of that particular level. Now in this question they are asking to calculate the 0 point energy, means that is the lowest energy level where the V vibrational quantum number is equal to 0. So if we put V is equal to 0, then 0 point energy EV is equal to, means E naught is equal to H nu divided by 2, where the H is the Planck's constant, nu is the frequency in hertz. But actually in the given problem, frequency in hertz is not given. In place of that, it was given frequency in centimeter inverse, means 2885 centimeter inverse. So because of that, this energy expression we can convert it into the frequency in centimeter inverse by replacing frequency in hertz. Nu is equal to C nu bar, where C stands for the velocity of light, nu bar stands for the frequency in centimeter inverse. Now putting all the constants and the values given in this problem, V is equal to Planck's constant, means 6.625 into 10 to the power of minus 34 joule, into velocity of light, means 3 into 10 to the power of 10 centimeter per second, into 2885 centimeter inverse divided by 2. If we calculate this, it comes 0 point energy, means the lowest energy level 2.8697 into 10 to the power of minus 20 joule. So this option is given in the B. So therefore in this case the final answer is B.